Hey guys, I just thought I'd give you some hints on practice problem 7.4.1. So this is kind of a fun problem if you ever want to design a recyclable can crusher. So what we've got here is we've got an arm that goes from point A up to point B and then over to point C, and we've also got a link here from B to D and a little piston head at point D that can go down into the cylinder and crush whatever can you put in there. And they give us a few things. They give us the force applied at C. They also give us length 1 and length 2. And these angles, they give us theta right here between the horizontal and AB. And they also give us theta, or sorry, phi between the vertical and BD, and alpha between the horizontal and BC. So what they want us to find then, they want us to find the magnitude of the vertical component of the force exerted at point D. So basically what's going straight down to crush this can. And then they also want us to find the reactions at A. So imagining this is like a design problem, what we might be saying is, okay, what kind of bearing do we need to buy at point A to be able to handle the kind of forces we're going to be putting on this? And then is the force going to be enough, with this length or whatever our design parameters are? Maybe we're trying to optimize something or we're trying to decide how long to make L2, for example. And we're saying if this is how much force the average person can put down at F, is that going to be enough force at D to crush the can? So this is kind of a fun practical example of how you could use statics in a design sense. If you know a few things and then you're going out and you're trying to make real world decisions about materials or purchasing things or ergonomics of like designing this for a human to do, or trying to make this so that maybe a small child could do it instead of having to have a bodybuilder pushing down at point C. uh, Being able to set up your problem, especially using something like Mathematica, where you can change a bunch of variables really quickly, the value of them, this could be really useful. So let's jump on it. We've got our given values here. We've entered those. F is, in this case, 50. L1 is 4. L2 is 20. Theta is 55. Phi is 15, and alpha is 20. And remember, just hit Shift Enter to get those to evaluate. I've already gone through and done it, so uh, I've already hit Shift Enter. They would be blue beforehand if I hadn't done that. But so we just talked about what they want us to find. Now, normally in a situation like this with a mechanism like this, what we'd want to do is break it up into different pieces and then analyze each piece kind of separately as its own with its own free body diagram. So what I would normally do in a situation like this is take ABC, this arm, and analyze that as its own with its own free body diagram, BD as its own free body diagram, and then D. So kind of take each piece apart, look at all the forces on it. We're going to have a force in the X direction, a force in the Y direction here at A. Obviously we've got F, and then BD is interesting because if you look at it for a second, you might recognize, and this is kind of cool to get to apply this here, BD is a two-force member because we've got a pin here and a pin here. And we know there's going to be force coming in and force coming out, and it can only go along it, so it's a two-force member. And that's going to make things a lot easier for us because when we draw, for example, ABC, then it's going to look something like this over here where we're going to have an X and a Y reaction at this pin joint. We're going to have F being pushed down over here, and then along BD we have just this one force. We don't have to draw an X and a Y force here, although we could. It would just make things more complicated to solve. So instead of doing that, we can make things a little bit easier on ourselves and just draw this force along the BD. Now, technically, you could draw that either way. It would just make it, again, a little bit more complicated as you go to solve it. So I drew it this way. And I got a little bit of guidance on how to draw my free body diagrams from a really great example in the book. If you look at example 6.13, that gives a good example on this. It's actually a great example overall. But go ahead and look at that. In my book, it's on page 299. It might be different in your book. That's example 6.13, sorry. Um, so once we've got this diagram drawn for this first piece, we could have started with BD or D with the piston head or with the link, but I chose to start with the handle, and I think you should too. You might be glad you did. So once we've got that, then we can sum forces in each direction, and we can sum moments to try and solve for the unknown forces that we want to solve for. I would advise trying solving for moments first, and I would try at about point A, just because that will eliminate these two forces. We won't have to consider those in our moment calculation, and it just works out really well. So I'm just going to tell you that kind of straight up. So let's start by summing moments about point A, and this can get a little bit complicated, so I'll kind of walk through it with you. And remember, a moment is a force times a distance. So starting at point A, and I'm just going to kind of walk out to my first force that I find, and that's going to be force in the BD. So a moment is a force times a distance. So the force is BD, but I want to break it down into components. So let's try taking, say, the vertical component of BD. That means I need to take the cosine of angle phi and multiply that by BD. So cosine of phi, and remember we have to use this keyword degree in here to get it to give us degrees instead of radians, or calculate using degrees instead of radians. And then, so this whole thing right here is the vertical component of the force in BD, is what that says basically. And then we want the distance. So the moment arm distance from A to point B is going to be this horizontal distance. So imagine a right triangle that includes L1 coming down from B and going over from A. So we want the horizontal component of that. So that's going to be cosine of theta times L1. So that's one moment, and that's going to be a positive moment. If you can imagine, that's going to try and turn the handle about point A in a counterclockwise direction. So that's positive, as far as moments go. And then the next one is going to be from force BD, but going in the x direction. So that's going to be going from right to left here. And so we kind of have to do the opposite. We're going to take the sine of phi, again, remember your degree keyword there, times FBD. That's our force for this next moment. And then the distance that we're going to multiply by is now going to be the vertical distance from A to B. So now we're going to take the sine of theta times L1. And that also, if you can imagine, is going to be positive, a positive moment, because it's, again, trying to turn the handle about point A in a counterclockwise direction. The next one, so that's where this positive sign comes in for this moment. And then the next one, you can see I put negative, you'll find out why, is from the force over here. The force is going down, and the distance is going to be the horizontal distance from A all the way over to C. So the way we have to get that is we have to combine a couple things. We have to get the horizontal distance from B to C first, and we do that by taking cosine of alpha times L2, and then we have to again get the horizontal distance from A to B, so cosine of theta times L1, and we combine those together. So here's our force for that final moment, and here's what we just talked about for the distance, and it's negative because it's going counterclockwise, or it's going clockwise about point A. So that's going to get us that, and I should have restarted Mathematica, sorry, so you could see this, but it turns out that in all of that, which looks like a lot, the only unknown is FBD. We know everything else. We know what phi and theta are. We know what F is. The only thing we don't know is the force in BD. So that makes it really easy for us, because then we can come down here and just solve. We can use our solve command in Mathematica and say solve for some of the forces in MA, what we called this whole thing up here, set it equal to, with a double equal sign, 0, and then solve for FBD and give it to us in a nice simple format with //n, and it's gonna be cantankerous because I already put it in. But anyway, it comes out to be 344.108. And so then I can set that as a variable. I can say FBD equals 344.108. And since I know that now, it makes it really easy to go in. And so if I know the force in BD, the first thing that it asked for over here was the force applied at D in the vertical direction to the can, right? So if I want to find that, I know FBD and I also know this angle phi, so I called my the force in the y direction just FBDY and used cosine of phi in degrees times FBD, and that gives me the vertical component, which turns out to be 332.383. And so that's the biggest part of the problem solved right there, which is really nice. Now you might ask, well, hey, wait a minute, we didn't use a free body diagram of BD or of D, and that's true, we didn't, but that's the nice part about two force members, is we don't have to, because we know that the force at B is also going to be the force at D. It's just going to be equal and opposite, but since you kind of do two equal and opposites and you're back to the same thing, because we have equal and opposite of this in this free body diagram is going to be pointing down in the BD free body diagram, but then on this end it's going to be pointing up, and then in the D diagram it's going to be pointing down again, so it's the same thing. So it's all good. We can just go with the 332.383. And if you want to see that in a little bit slower motion, what I just explained, I'd look at example 6.13 in the book, because just the diagram on the front page of that example shows it pretty clearly. So next it wants to know the forces at A, so AX and AY. And these are going to be really easy because of what we've already set up. So let's start with X, why not? So we sum the forces in the X direction. We've got FAX, which is unknown for us. I should have restarted that, so this would be blue for you. But anyway, that's unknown. And then we have the Y component of FBD, which you can see, or the X component of FBD, sorry. So that's going to be the sine of phi times FBD. And then we can just actually, since this is the only unknown and this is a really simple equation, I just rearranged it and said FAX is equal to sine of phi times FBD, and we get our answer. And then we do something really similar in the Y. We just say sum of the forces in the Y is equal to FAY minus F plus cosine of phi times FBD, and then rearrange it, and we get it. So let's plug those in and make sure we got everything right. So at D in the Y direction, 332.383, what we found up here, if you remember. And then at A in the X direction, 89.0617. And A in the Y direction, negative 282.383. And let's check it. Hey, there you go.